Welcome viewers to the massive open online course on Cartographic Techniques Practical. Today we will be dealing with a topic called the hypsometric curve. Today we will be seeing in detail on how we can derive a hypsometric curve manually. If you are a complete beginner, please be at ease because we will be starting from the very beginning and going all the way to how we derive a hypsometric curve. So, before we dive right in, we will have an overlook of what today's content is. First, we will have an introduction to what the hypsometric curve is. Then, we will see what its practical uses are. Next, we will move on to the manual derivation part, and finally, we will conclude with the practical real-life uses of hypsometric curves. Like a lot of terminology that we employ in geography and cartography, hypsometry also has its roots in Greek, specifically a word hypsos, and then it's followed by metrons. Basically, it just means measuring depths or elevations. Put together, the word has slowly evolved to what we know today as hypsometry. Also, in the modern sense, hypsometry is believed to have been put forth by Stoller, who is also popular for studies including hydrology and related features. Okay, so what does a hypsometric curve basically do? It is a graph that shows the distribution of the horizontal surface area with respect to elevation. Basically, it will tell you how much area falls under a certain category of elevation. So, what it does is, it works by showing you on a graph such as this. On the x-axis, we have the relative area, and on the y-axis we have elevation. So, this particular graph here, these points here will tell us how much area falls under what elevation category. So, why do we use hypsometric curves? So, hypsometric curves will allow us to understand and compare how landforms have gradually evolved. How can just a geometric curve explain things, you might wonder? In simple terms, hypsometric curve has three distinct shapes. One is a convex curve. In case of a convex curve, the top is steep. In such cases, it suggests that the landform is young or it's in the early stages and haven't been eroded much. So, in the second case, what happens is the curve takes an S shape, and here this indicates that the slope is mature. There is a balance between erosion as well as uplift. Now, we move on to concave or the flat top and steep bottom case. In this scenario, it points to an old, please remember, a concave curve means a flat top and a steep bottom, and this marks a very old landform where erosion has been thorough and most area are at the lower elevation ranges. So, let us have a recap. First is a convex curve, which means there is a very steep top. Like I said, the convex curve has a steep top. It means it is young and there is active erosion in these regions. The second scenario is an S-shaped curve, which indicates a mature landscape. It means that erosion and uplift are both balanced in these areas. And finally, we have the concave. In this case, the top is flat and the bottom is extremely steep. indicating that this is an old landscape and the majority area lies under lower elevation. So, what we have been waiting for is the manual derivation of a hypsometric curve. So, let us get right into it. Since this is a practical exercise, it would be great if you can follow along, but since I have done my work beforehand on the background, I suggest you look into tracing your items first. So, you are going to require a few materials. The first one is your topographic sheet. The next is a tracing sheet. Then you will also need a graph sheet and you will need pencils, rulers as well as color pencils, and a calculator if you hate doing mental math. So, now we will dive into the method part. We are splitting our method into 5 steps. We are splitting it into exactly 5 steps. I think the third step is going to seem fun. So, in the first step, we will prepare and define the elevation bands on the map. In the second case, we will be tracing our contours onto the tracing sheet. In the third step, we will be counting grids. In the third step, we will be counting the grids to calculate the area. And in the fourth step, we will calculate the relative values as well as the areas. Now, in the last step, we will finish by plotting the graph. So, for your first step, you are going to take your topo sheet and choose a study area. By choosing a study area, it is better that if you choose a smaller area, maybe something irregular like this. You pick a very small area and you outline that first. Next, you are going to note what the contour intervals are. So, in most cases, we will be using a topo sheet that is a 1:50,000 scale, and in some cases, you might end up with a 1:250,000 scale. So, in both these cases, for 1:50,000, the contours are usually at 20-meter intervals. So, in the case of topo sheets that are on a 1:50,000 scale, the contour intervals are usually 20 meters. And if you carefully observe in the bottom part of your topo sheet, you can see the scale as well as the contour intervals. And similarly, in case of 1:250,000 scale, the contour intervals are usually set at 100 meters. Now that we have defined a study area and marked the contour intervals, we find the lowest and the highest elevated point. By the lowest and highest elevations, we mean if your area has a contour that is marked at 1000 meters and the lowest contour is marked at 300, you are going to need to keep in mind both 300 as well as your 1000-meter contours, because these are your highest and lowest values. And we will be using these very bands to define your elevation bands or categories. Your contours are going to help you define these elevation bands. Moving on to the second step, tracing. In the second step, what we are going to do is these contour lines that you see on your topo sheet, you will be tracing those on to your tracing sheet, and these contours will have values. So, when you are tracing it, please make sure that the boundary is marked preferably with thick lines. Please note, when you are marking your boundary, you are tracing it onto your sheet, please use thick lines. And for the case of contours, make sure that they are marked using very thin points. And one more thing that needs to be kept in mind is that as you trace your contours, you have to label them with their values. If it is 300 meters, you label it right away as you trace. Now that we have our contours traced, we have our next step. And for this next step, we are going to take our tracing sheet and put it on top of your graph sheet. Remember, we had mentioned earlier alongside the materials required that we are going to require a topo sheet, a tracing sheet as well as a graph sheet. Once you have traced your images, you put the tracing sheet on top of your graph sheet. This makes our third step easier. And coming to that, third step is counting grid squares. So, what we are required to do now in this situation is, I have my contour line marked here. Let's say this is the contour I have chosen and this is my highest at 1200 meters. I am going to start counting my area from this area above this particular contour. Now I am going to count my squares here, and in this scenario the square that I am using is a 1 millimeter into 1 millimeter small grid, which means this larger square, which means the larger square here is 1 centimeter into 1 centimeter. Please note, in most cases your graph sheets will have larger squares that are 1 centimeter into 1 centimeter and the inner grids will be a millimeter each. So, when you are trying to calculate an area, you are first going to count the number of squares. So, in this scenario, let us say I am using a topo sheet of 1:50,000. In this case, what happens is 1 centimeter on map equals half kilometer on ground. So, when you are using a topo sheet of the scale 1:50,000 and you are using a graph sheet, what you need to keep in mind is that one big grid on your graph sheet is going to represent half a kilometer on actual ground. In most cases, for simplicity, to avoid the complication with the half kg part, what we do is we take two grids together like this. So, since 1 equals half kilometer on ground, we are going to take 2 together and that will equal 1 kilometer. This makes calculation easy for us. So, in this scenario, what is going to happen is you will count your squares on top of the chosen contour. This will later help you calculate the areas. So, we are starting from the highest and we go down lower, the next contour here. So, basically we are going to count the area above this first, then we are going to count the area together for these two. Then as we count, we are going to count the area for all three together. I have a table lined up for you in case you are confused right now. So, now we are going to count the squares and mark that in a table. And this is, this is what I meant when I said count cumulatively. First, you start from the highest value, you count the area above it in terms of squares, then you come down to the second one and so on. And in the end, the last stage for this step is you estimating the partial squares consistently. This is something that we will all struggle with initially. By partial squares, what I mean is something very simple. In this case, I have tailored the image for that not to happen. But if you look carefully here, you can see that in this case, these tiny squares, only one line of those squares are included. So, if you are patient enough, you can count your millimeter squares first. This will allow you to calculate the area more accurately. Now, we will move on to step 4, calculate the relative values. So, in the earlier step, what we did was count the number of squares above a certain contour value. Now, what we do is, we know that the scale is 1:50,000, which means we need to take a grid that is 2 centimeter into 2 centimeter. In this scenario, what happens is, inside of these 2 centimeter side square, we have 400 smaller squares. So, when you are estimating the value, you count the number of squares and employ your math according to the scale that you have. So, once we calculate the area based on the number of squares, we will have a table that looks somewhat like this. So, this is a sample data that I have prepared earlier. Here the elevation values range from 0 to 4000. In this scenario, 4000 being my highest contour value, I have the least area that falls above it, which is 25.34 square kilometers. And similarly, the lowest value I have is a 0, and hence the total area lies above this given contour value, which is our lowest. So, the total area we have here is 1785 square kilometers. Now, you need to know each segment, the area that comes under it, as well as the total area of your choice of study area. In this case, we have both. Under each category, we have it, and we have a total of 1785 square kilometers. So, once we have both these values, we can calculate the relative area. Don't worry, the formulas are right here. So, what we want to find now is the relative area, and to find the relative area, this is going to be marked in percentages. What we do is, we take the cumulative value, which is 25.34, then we divide it by the total value, and whatever value we arrive at after this calculation, we multiply that with 100. So, this will give you your percentage values, and similarly, we will execute the same for each contour values. As is bound to happen, the highest contour value will see the lowest percentages in case of relative area, and the lowest, which is 0, will see the entire area being above it. Now that we have these calculations marked, what we move on to next is the plotting. As I said before, please keep in mind, based on your scale, this can be 1 square or this can be 1 square. And again, please do not forget your partial squares here. Once again, how we calculate the area is based on the scale as well as the number of squares. If your scale says 1:50,000, for example, you will be using a 2 into 2 grid like this. Like I said, 1:50,000, your grid is going to be comprised of 400 smaller squares. Alright. Now, how do we derive a hypsometric curve? Once we have our elevation in meters sorted, after we have drawn our contours and we have calculated our relative area in percentage, please allow me to take you back to the table for a second. Here we have a relative area. It is derived in percentages. Please do not forget, relative area has to be taken in percentages and the calculation is as follows. So, once we have our elevation data as well as relative area sorted, we are going to move on to deriving our curve. What we do is we draw our graph, the x and the y axis, and it is preferable that you plot area along your x axis and the elevation around your y axis. Please do not forget, when you are plotting for better results, it is better that you mark relative area along your x axis and elevation around your y axis. Now, we are marking each point corresponding to the values. We are plotting those. In this scenario, it is easier that I show this on screen while you are doing it at home. It is better that you use graph sheets instead of drawing grids on your own by pencil and scale. So, once you have these points plotted, the next step is to connect these points gradually in a smooth line. Please make sure not to use a scale when you are trying to plot the lines. When you are trying to connect the dots that you have plotted, please use freehand drawing and please make sure that you draw it steadily. In this case, I have ended up with a curve that has a steep slope towards the bottom areas and the top isn't as steep. What kind of a curve do you think this is? Please ponder on it while we move on to the next part. Once the curve is derived, the next step is interpretation, and based on the first part where we mentioned the convex, the S-shaped and the concave, please think what this particular curve belongs to, what category this particular curve belongs to. So, once again a reminder on how to handle partial squares. If you have smaller squares that are only covered partially by a particular contour line, you can either choose to count a quarter of it, or you can choose to combine all such similar squares where it is partially covered until it makes one full unit. So, this is something you can do. Not completely interested in counting each millimeter square, you can make sure that the partially covered areas together are counted and they make one unit. So, the next part is counting the millimeter squares, and the reason why I am reminding you of how to count these squares is simple. When you are doing something manually, the chances for errors are very large, and in this particular case, if you miscount your squares, you are going to be way off reality when you are calculating the area. So, to avoid this is why I am again reminding here on how to count the squares. So, this is one method of minimizing errors, that is to count the millimeter squares. If you are counting the millimeter squares, chances of errors are minimized when compared to counting squares that are each a centimeter or more. So, please make sure that you are consistent with your methods. Now, we will see what the practical day-to-day uses for hypsometric curves are. Now, we have watershed comparison, then tectonic analysis, crustal studies, erosion assessment and flood prediction, followed by what exactly is planetary comparison doing here? You might wonder. Let me make this clear. Geography has multiple uses, and if we are to categorize them, you can include comparison of watersheds, Now, we are going to see what use watershed comparison is. We need to know how much water a watershed can hold, and this allows us to have a grip on quantifying the water resources available to us. The next one is tectonic analysis. If you are interested in news, you might have observed that a lot of European countries, Russia and the US have been experiencing earthquakes, and certain areas in the Pacific have seen increased volcanic activity. So, by tectonic activity, what we mean is the earth surface's movements. These movements can to an extent be predicted or forecasted if you have an idea of how the shape of the earth on the surface that we have access to changes. That is where hypsometric curve comes into play in case of tectonic analysis. And what use is predicting it? Of course, a lot of lives and property can be saved through early warning systems, and this provides the base for that. The next one is crustal studies. Again, this helps you study the movements and patterns of these movements, so that sudden movements can to an extent be understood beforehand. Next, we have erosion assessment. If you have participated in quiz competitions or essays or anything related to the environment, this is one term you are bound to have come across: erosion. Erosion is nothing but the process of topsoil or top layers of the earth's surface being taken away by means of water or air. So, erosion assessment helps you identify the age of a certain area and how much volume of topsoil is eroded. So, this will also allow you to counteract these cases if it is extreme, provide protective measures to protect agricultural lands, and also in case of deserts where sandstorms are the major reason for sand to be eroded or moved, the direction can be studied based on the direction of how the curves or how the contours are formed. Continuous study will allow you to predict which areas this will move to and also counteract it through multiple measures. Next, we have flood prediction. If you have lived in Tamil Nadu, you know what floods can do. They are not something everybody looks forward to, instead it is something we all dread. So, again, today the hypsometric curve that we looked at was exclusively for land surfaces. So, there are variants where you study the ocean surfaces as well as the ones where you study drainage basins. The hypsometric curve that you draw up for drainage basins as well as the oceans allow you to study the pattern of the water, the effect it has on the landforms underneath it, as well as in cases of rivers, how the water might rise and fall seasonally if you observe the contours enough. So, this will allow us to foresee areas where floods might happen, or in cases of floods, areas that might overflow. Planetary comparison seems like something out of this world, keep the pun, but it has been observed that scientists first, when observing planets outside, like other than Earth, for example, let us say Mars, when the scientists are first going to a new planet, they set their rovers out, they measure the elevation changes, and they use this to compare the surface of said planet to that of Earth. This allows them to study and identify the differences and similarities between the said planet as well as Earth. Before we wrap up, let us have a look at what we looked at today, the key takeaways. One is that understanding of terrain analysis fundamentals. First, when we say terrain analysis, one part is studying the land, then another is studying the rivers, and the last the ocean. Here we have studied the land surfaces alone. And we have a basic idea on how the study goes. The next part is the process. Collecting elevation data, calculating areas, normalizing values as well as plotting the curve. We have seen that the curve provides insights. We have seen that the curve that we derive gives us basic insight into what stage of evolution the said landform is at and the processes that might be involved. Next, we have the Earth's global curve that reveals the planet's crustal structure and a signature of plate tectonics. So, despite challenges, manual derivation builds critical skills for terrain interpretation. In short, even though the method is pretty long and the chance for errors are plenty, this will keep us closer to how terrain analysis goes. So, that will be all for today's session. Thank you.